So let's talk about the mean free path. So mean free path um, is the is the average distance a molecule travel between collisions. So this is what if you have a gas molecules in this container. So this is the container. Okay. So there may be a lot of gas molecules like this. You know that these all are actually moving at random motion. Okay. So for example, this molecule could could go to collide with this molecule, and finally after colliding that it could collide with other molecules, and after this it could collide to other one, so it can go in the random order. So this means this is the average distance of molecule travel between the collisions, so we have to take the average distance. Okay. So the actual formula to find the this mean free path we generally write as equals lambda equals p times t mean. This is the mean time of the collision. So this is the mean time of collision. This is the mean time of collision, and this v is actually the speed of molecules. This is the speed of molecules. Okay. Then this can be written as equals p over 4 pi, okay, under square root 2 r squared n. Okay. So here there are some of the terms we need to define. So this is this symbol lambda is for the mean free path, and this p is actually the volume of the gas. This is the volume of the gas, which is equal to the volume of the container. Okay. And here r is the radius of the molecule, radius of molecules, and this n represents the total number of molecules. This is the total number of molecules of gas. So using that expression, we can find the mean free path for a given gas molecule. And clearly it depends upon the volume, it also depends on the radius, and it also depends on the number of atoms present in this container. So based on this, based on the kinetic theory of gas that we have done so far, so this also gives it's called the Maxwell-Boltzmann distribution of gas molecules. Means if you plot a graph of V along the axis X and the probability is along the axis Y, we can get this kind of plot. Okay, so you can see that when velocity is 0, probability is also 0. If the velocity of the gas molecules increases, probability of finding is also increasing. So you get this kind of curve. Okay, like this. So you can see that our PRMS is actually lying in this region, and slightly at the top, this is the PP, and this is the PP is actually the most likely speed. So this is slightly less than the P mean. Okay, so this graph is for oxygen molecule at temperature 300 degrees Celsius. Means if you change the temperature, means if we change the temperature, or if we change the gas, the plot will also change. Okay, it will not be the same. But you see that PP and PRMS values are very close for a given gas at a given temperature. So this is the same plot but for the different temperatures. So again, V is plotted along the axis X and probability is along the axis Y. But say in this case, temperature T2 is higher than T1. So if you see in the plot, with increase in temperature, at higher temperature, the speed of the molecules will also shifting towards the right. If you see it here, this is there, and this is Vp position shift. So Vp is here, maybe Vrms will be here. For that temperature, Vp value is slightly different. It is Vp prime and Vrms prime for that temperature. So it also shift towards the right. So this is called the Maxwell-Boltzmann distribution. So we can write this in the form of equation. So the Maxwell-Boltzmann distribution actually tells you that the motion of molecule in a gas is random in magnitude and the direction for individual molecules. But a gas of many molecules has a predictable distribution of molecular speed. This predictable distribution of molecular speed is known as the Maxwell-Boltzmann distribution. Okay, so for that we have, I'm going to write the equation how the Maxwell-Boltzmann distribution looks like. So yeah, so we write the equation V is actually the function of speed, which is equal to 4 pi times m over 2 pi kt power 3 over 2 v squared e negative m v squared over 2 kt. Okay, so this expression is called the Maxwell-Boltzmann distribution. So in symbol, this Fp basically represents the function of the Maxwell-Boltzmann distribution. This represents that. Okay, so in this case, you see m is the mass of the molecule, mass of a gas molecule. Okay, gas molecule. And here you can see here that this T is the temperature, but be careful that is absolute temperature, means the temperature should be recorded in the Kelvin scale, means the temperature in Kelvin scale. This means, and you can see here this V is the molecular speed, okay, and I believe we defined everything, m k t, and we have k is the Maxwell-Boltzmann constant, or we also call it the Boltzmann constant. So this means this is the plot that you see before. If you plot P along the axis X and this function, distribution function, means probability along the axis Y, you get the curve up like this. Okay, so this curve is actually plotted from this equation. Okay, let's second talk about phases of matter. So in general, we have, you know that we have three phases. This is the solid, that is the liquid, and the gaseous state. Okay, these three phases. So this phase of matter will depends on it changes with temperature, it changes with pressure. Okay, but at sometimes, depending on the phase boundaries, we call it phase boundary, two phases of matter coexist. It means that two depends on the phase transition taking place. But we call the triple point. Triple point is the point at which all phases coexist. All means every solid, liquid, and gas phase coexist. Okay. Then let's see here the plot that we have seen before also. This, if you see um, here, it phase boundaries, phase boundaries. This is the phase boundary for liquid and this vapor. Okay, this means if you consider one particular point over here, what will happen if you increase the pressure at this temperature? If you increase the pressure, then it converted to liquid. If you decrease the pressure, it will be the it will be in the state of vapor. Okay, so this is the line, boundary line, where liquid and vapor phase coexist. Similarly, you will see here the other phase. In this phase, you see that two phases. One is the solid, other is the liquid. These two phases coexist. So this means in this boundary line, both solid and liquid phase coexist. This means, say for example, say just I'm taking one example. Say you take one constant pressure here. If you increase the temperature, keeping the pressure constant, it will go to the liquid state. If you decrease the temperature, it will go to the solid state. Similarly, we can consider the effect of pressure at a given particular point. Okay, and the other part we have here is this one. You see here, this is also the this is also, we call it the what's called the phase boundaries. As phase boundaries, if you go upward from this point, then we are in the solid phase. If you go down, means if we are going to decrease the pressure, it will be in the liquid. Sorry, it will in the phase of vapor phase. So if all these lines could meet at a particular point where all phases coexist, is called the triple point. So at this point, all phases coexist. Okay, but there's another point over here. You see, this is the critical point. After critical point, you see that all phases it will be in the gaseous phase. Okay, so that's how we defined already before, I believe. So this you see in the picture, the dotted green line is meant to replace the solid green line in the corresponding phase diagram. Okay, so this phase diagram is different for different substances. So this phase diagram is for water, but it could be different for CO2 gas, it could be different for the other gases. So this is some other further resources you can look at when you get the free time. There are many great resources you will find, but always when you are looking a lot of resources, you have to always consider the time management. This is the great issue, time management. Okay, so my idea is this: you have to follow the book. It will be the best option. Follow the textbook, and you have to look at the other materials based on the topics of the textbook. It will help you to understand. If you go through a lot of resources at a time, you may get confused. Okay,